Hey everyone, let's jump right in. Today, we're tearing down two absolute foundational architectural patterns from our source material. These are literally the engines powering the speed and scale of the modern digital world. So get ready for a fast-paced explainer on how complex systems actually operate behind the scenes. Let's do this.
So here's a question for you. How do massive digital systems process mind-bogglingly complex tasks so incredibly fast? We all know linear processing is a huge bottleneck, right? If your cloud platforms process just one step at a time, they'd be, well, frustratingly slow. So how do these systems actually handle massive scale? Engineers had to completely rewire how work gets done to stop our everyday apps from just grinding to a halt.
Right off the bat, our source material makes it clear that these solutions are universal. We're not just looking at some niche software trick today. No, these are essential, foundational designs used everywhere. We're talking programming, massive server infrastructure, and honestly, even down to the physical electronics and microchips powering the device you're using right now.
What's really fascinating here is how the source breaks this core architecture down into a brilliant duality. On one side, you have fan-out, which is all about dividing the task. And on the flip side, you have fan-in, which is entirely focused on aggregating the results. It's crucial to look at these not as competing ideas, but really as two halves of the exact same process. They work together in perfect harmony.
Okay, let's zoom in on that first half. Fan-out is basically an architectural pattern that takes a single task, or maybe a massive chunk of data, and divides it. And here is the absolute genius of it according to the text. It doesn't just sequence the work. It violently splits that workload into multiple parallel streams. This means completely different parts of a system can attack the exact same problem at the exact same moment in time. The phrasing in the text really nails it. It says it divides a single task or data into multiple parallel streams. Just think about the sheer elegance of that design for a second. Instead of one single overworked processor groaning under the weight of a massive job, the system just creates instant, simultaneous action. Everybody pitches in at once.
Let's ground this with a simple analogy. Imagine you're looking into a wildly busy restaurant kitchen. The head chef gets this massive, complicated order for a table of 8. Now, if that chef cooked every single item sequentially, one by one, those customers would be waiting for hours. So the chef divides the order. Suddenly, the grill station, the fry station, and the salad station are all cooking their specific parts at the exact same time. That right there is fan-out in the real world.
But as the text rightly points out, dividing the work is really only half the battle. If the food just sits there at the different stations, the customer goes hungry. And that brings us to the second pattern, fan-in. Fan-in is a pattern that aggregates the results of those parallel streams back into a single response. So while fan-out scatters the workload from massive speed, fan-in is all about gathering, organizing, and unifying that completed work. Check out the specific language here. It aggregates the results of these streams back into a single result. Aggregation is literally the star of the show in this phase. Because think about it. It absolutely does not matter how fast your parallel streams process data if the system can't bring all those scattered puzzle pieces back together perfectly at the end. Going back to our kitchen analogy, this is exactly what fan-in looks like. First, all those cooking stations finish their specific parallel tasks. Then, the head chef gathers all those separate components from around the kitchen. And finally, the chef carefully plates them together into one cohesive, amazing meal to send out. Those separate streams absolutely have to merge for the final product to exist. And this brilliantly illustrates exactly how these concepts apply to modern computing. We can easily take this simple kitchen analogy and map it directly onto the complex world of software architecture. When we're talking about huge cloud applications today, those separate cooking stations, well, engineers actually call those microservices. Let's break that down. So, in a real digital environment, say you click Buy Now on your favorite shopping app. Boom, that single user request is instantly split into 3 separate streams. One microservice handles user authentication, another simultaneously runs a database query to check inventory, and a third talks to the payment gateway. One request just fanned out into 3 parallel streams. And because these 3 microservices are operating simultaneously, thanks to our fan-out pattern, the total time it takes to process your purchase is literally a fraction of what a clunky, linear system would take. Imagine if the app had to authenticate you, and then wait to check the database, and then wait to process the payment sequentially. That loading spinner would drive you absolutely crazy.
Parallel processing fixes that. So, pulling all of this together, here is your complete microservices lifecycle. Step 1, a single complex task arrives from the user. Step 2, the fan-out architecture rapidly splits that task into parallel streams to save time. Step 3, once those individual microservices do their thing, the fan-in architecture steps up to aggregate the results. And finally, step 4, a single unified response is seamlessly delivered back to you, the user. I really want to emphasize this single idea. 1. Because despite all the insane parallel routing happening behind the scenes, and despite potentially dozens of microservices talking across different servers, the system is fundamentally designed to always return exactly one final aggregated response to you. All that incredible complexity is just completely hidden from the user, because the handoff between fan-out and fan-in is so perfectly orchestrated.
Which brings us to a final, pretty provocative thought for today's explainer. If your digital system brilliantly divides a massive task, executing an absolutely flawless fan-out, but it fails to aggregate the results properly during the fan-in phase, did it actually solve the problem? The answer, of course, is absolutely not. These two architectural patterns are strictly, undeniably dependent on each other. Master how they work together, and you've unlocked the true scale of modern computing. Thanks for joining me for this explainer, and keep questioning how our digital world is built.